We're going to now study complex numbers. Complex numbers are a new type of numbers that we haven't experienced before. Before we get started on that, it's worth just thinking about what numbers are and what numbers we're used to seeing. We're used to things like the counting numbers, natural numbers from 0, 1, 2, 3 and so on. Add to those the integers, which adds on the negative of the natural numbers, so we have -2, -1, -20, +20 and so on. These numbers come about fairly naturally. We can also divide integers by integers to form the set of rational numbers, and also you can see where these come from as well. What about irrational numbers? Where do these come from? Well, actually they come from quite an unexpected place. They come when we consider geometry. When you define geometry, we start thinking of things like exactly straight lines, exact right angles, exact circles, and things like this. And once you have things like a right angle triangle, one is forced to look at irrational numbers, such as the square root of 2. If you take a right angle triangle with sides of length 1, the hypotenuse is equal to the square root of 2, and it's relatively easy to see that this does not exist within the set of rational numbers. You can't write it as a fraction. The same is true for the number pi, and in fact there are other irrational numbers that are forced upon us, like the number e, which actually we've seen comes from calculus. So irrational numbers appear when we have this idea of geometry, the idea of exact circles and so on, and in fact we've seen that the real number line is incredibly important when we define things in calculus, like continuity. It's essential for defining the derivative and so on. This idea that you can move smoothly along the real number line from one number to the next. So what's wrong with the real numbers? Why do we need anything else? Well, it turns out that in the same way that geometry implies a new set of numbers beyond the rational numbers, actually algebra implies that there should be a new set of numbers as well. Let's consider the pair of equations. Only one of these has a solution. But why is that? It's because we're used to dealing with the real numbers. We're quite happy to write down the solution to x squared equals 1 as x equals plus or minus 1. But we're not happy trying to solve the equation x squared equals minus 1 to give us x equals plus or minus the square root of minus 1. Well, why not? Because the square root of minus 1 doesn't exist within the real numbers, we obviously can't do that within this number system. But if we just step back and say, okay, let's just pretend that the square root of minus 1 makes some sort of sense, we can actually solve all polynomial equations. So for example, if we look at the equation x squared plus 2x plus 2 equals 0, that implies using the normal formula for the solution of a quadratic equation. And this works in the sense that if you take this solution, either of these solutions, and substitute them into the equation that we start with, it satisfies it. As long as we just pretend this number exists, it seems to work okay. And so that's the basis of complex numbers. We just pretend this number exists, square root of minus 1, and carry on and see what happens. And in fact, by allowing for complex numbers, we actually open up ourselves to much more elaborate theories. For example, in physics, quantum mechanics has to be formulated with complex numbers. So they're incredibly important, and yet they arise from this rather strange notion of just insisting solutions to polynomials exist. Let's define this number, the square root of minus 1, a bit more carefully. So we define what's called the imaginary number I, such that I squared is minus 1. This is not a real number. I does not exist within the system of real numbers. And we also define it via the equation I squared equals minus 1, rather than saying I equals the square root of minus 1. I doesn't have a sign to it. It's neither positive nor negative. So trying to say I equals the square root of minus 1 versus minus the square root of minus 1 doesn't really mean anything. So we define it this way. And in fact, we can now add this to real numbers to form a complex number. So we saw the solution to the quadratic equation was minus 1 plus or minus I. So if we try and substitute this into the quadratic equation, which is where it comes from, we'll just choose a root with a plus in it. What do we get? Well, let's multiply everything out using the normal algebraic rules we're familiar with, grouping the i's together. Then what we see is that once we use the fact that I squared is minus 1, all the parts without an I cancel, and all the parts with an I cancel. So this gives us 0. So the rules for adding and multiplying all follow that of real numbers. And we define a number like this, a number of the form a plus ib, where a and b are real numbers, they exist in R, is called a complex number. The set of all complex numbers is called C. And we just add and subtract and multiply these in the usual way. Just some examples. If we multiply these two numbers together, then all we do is just multiply this out algebraically as we normally would, and we collect the terms which are real and the terms which are imaginary separately. So we have minus 21 plus 1 from the I squared, minus 3 plus 7 times I, and this comes out to be minus 20 minus 10I. Let's try this example, 3 plus 4i times 3 minus 4i. This comes out to be, so we notice the imaginary part cancels and we're left with just a real number, 25. If we multiply two numbers, a plus ib times c plus id, we have ac minus bd plus I times bc plus ad, where the magic of the number I has come in this minus sign. There's a few bits of terminology that go with complex numbers. For a number z equals x plus iy, where x and y are real, we call x the real part and y the imaginary part. And both of these numbers are real numbers. The symbols re and im are used to extract real parts and imaginary parts from complex numbers. And note that I times y is an imaginary number and y is a real number. So the imaginary part is actually real. So for addition, subtraction, multiplication, everything goes through as normal with the real numbers. So we just do exactly the same operations, but we keep the factors of I separate and replace any powers of I squared, with minus 1. What about division? Well, for division, we need a little bit more work. Let's think about the number 1 over I. What does this equal? To divide by the number I. Well, what I'm going to do is I'm going to simplify it the same way I would simplify 1 over a square root. I'm going to multiply the top and bottom by the number I. Then on the denominator, I get I squared, so this becomes minus I. So the operation of dividing by I is the same as multiplying by minus I. And in fact, we can use this trick for dividing by a general number. So if I divide by the number x plus iy, a general complex number, I'm going to multiply it by the following. And the reason I've done that is so that the denominator becomes a real number. So the denominator, when we multiply those two together, becomes a real number x squared plus y squared. And so 1 over z, when I factor it into the real part, has a real part x over x squared plus y squared, and an imaginary part of minus y over x squared plus y squared. So this writes the number 1 over z in what's called the Cartesian form when we write it as x plus iy. Now there's a special number that's appeared in this. This number x minus iy, which I multiplied and divided by, is called the conjugate to z. It's a very important number that we'll see come up over and over. We write the conjugate with a bar on it, so we write the conjugate as x minus iy. We flip the sign of the imaginary part and we stick a bar on top of it to denote this operation. So then what we've seen is that z times is the real number x squared plus y squared. And so we've written the number 1 over z as z bar over z bar. And that way it writes 1 over z in a Cartesian form, and it allows us to divide by complex numbers. Let's just do a quick example. If I want to simplify this complex number, I multiply the top and bottom by the conjugate of the denominator. It simplifies to 1 minus I. So the conjugate then is a very useful number associated with z. So we have seen then that complex numbers can be defined in a relatively straightforward way, and in fact they allow us to then solve any type of quadratic equation. They are very strange though, they're quite different from real numbers. So for example, The idea of ordering complex numbers does not exist like it does for the real numbers. In the real numbers, we have a real number line, and we're very used to thinking of that as increasing along the real number line, numbers getting larger. The idea of greater than or less than doesn't exist for complex numbers, and it's worth thinking a little bit about why that must be the case.